My webcam isn't working, but let me share my screen.
Okay, sure.
Yeah, Linux problems. Okay, can everybody see my screen?
Oh. Am I? Yeah, you can. Okay. Sorry, it's me. Yes, we can see your screen.
Okay, cool. So, all right. So, hi everyone. I'm Pratyush, and today we'll be me and Dave, who's also co-author of arkworks, will be leading a tutorial on SNARK development using our APIs in the arkworks ecosystem. So, at a high level, arkworks is a sort of Rust ecosystem for developing ZK snarks. We have, as you'll see, a lot of libraries spanning the entire sort of snark stack. The main repos are available here, and the tutorial is at this link. It should be public, the repo now. If it isn't, please let us know in the Zoom chat, or there's also a Telegram channel which you can find in the sort of the ZK Proof Workshop HackMD. But yeah, so basically arkworks is a Rust for ZK snarks. It's the work of a lot of excellent folks at Berkeley, as well as excellent contributors from outside. Okay, so let's dive in. So our goal in today's tutorial will be to build a zero-knowledge rollup. So what's a ZK rollup? It's basically a way to prove using zero-knowledge proof the correctness of a batch of transactions. So let's say I have these 4 transactions, TX 1, 2, 3, 4, right? What I would do is I would make a circuit which does 2 things. First, it verifies each transaction, which might involve some checks like signature verification, or checking balances, or checking commitments, or something else, or some other stuff. And so that'll be step 1. And then step 2 will be to check that the state transition that results from applying each transaction sort of is valid, in the sense that the output of transaction 1 is sort of the input state to transaction 2, and the output state of transaction 2 is the input state of transaction 3, and so on and so forth. And that the initial and final states are sort of match up with what's publicly known. So for example, you could think of like a Merkle tree representing the state. So the initial root and the final root would be publicly known, and the snark would check that these sequence of transactions sort of they lead from the initial root to the final root. Okay, so this, like, it seems in a high level way, it seems like relatively simple on paper, but actually developing such an application requires a lot of knowledge across a lot of domains, right? So you have to choose and implement your snark. You have to choose an elliptic curve for this snark. You have to design efficient circuits for all of the components inside your roll-up circuit, right? Like Merkle tree verification, signature verification, hash functions, and many other smaller things. Right? And finally, once you've done all this, you can finally go ahead and actually construct your roll-up, which involves now protocol design and all kinds of other tricky things. Right? And this is not just like limited to roll-ups. It's a common feature across sort of any kind of ZK snark application, right? So in Zcash, or in recursive snarks in Mina, or in sort of batch signature aggregation in Cielo, all of these places you have these sort of same challenges where you have to have a knowledge of a lot of domains, like finite field and elliptic curve arithmetic, proof systems, as well as constraints that you put into these proof systems, right? And so this requires knowledge of these many domains. And if you want your application to be both secure and performant, then you actually need to know each of these domains properly, right? So you need to know how to do algorithmic optimizations, know the security properties of your snarks are, how to implement primitives, and finally, how to implement your final protocol, right? And to make this worse, every few months, there's sort of new techniques in each of these domains, new kinds of curves, new kinds of proof systems, new kinds of arithmetizations, or, snark-friendly hash functions, and so on. So basically, keeping up with this task, keeping application up to date is, kind of a tricky thing. Okay, so the question then comes, like, how do we sort of control this complexity and enable the average person to come in and develop applications using ZK SNARKs, right? So our sort of idea in arkworks is to try and use this, very standard tool called abstraction, right? So what we do is we take sort of a step back from this in the weeds view, and we take, we zoom out and we try to abstract and find out like some main categories that each of these kinds of tasks belongs to, right? So what we do is we identify three kinds of sort of domains. The first is application development. So this is like actually constructing your application. And at this level, you're mainly concerned about, maybe you've already chosen your hash function or whatever, like like SHA-256 or Blake2S or Poseidon are like relatively secure. So you use these and you want to just be able to take these as sort of existing components and use them to develop your application. You don't want to have to reason about the elliptic curve or the proof system or that kind of stuff, right? This level below that is you're actually interested in doing SNARK R&D, right? So you're developing new SNARK systems, you're developing new arithmetizations, and at this point, you interface with both the constraint system and the elliptic curve level as well. At the bottom, you have your algebra. So this is people developing new curves and new kinds of polynomial arithmetic and so on, right? So this tutorial will be concerned mainly with application development, but the nice thing about arkworks is that it tries to sort of offer solutions for each level of the stack. So the lowest level, we provide these very nice generic libraries for finite field, elliptic curve, and polynomial arithmetic. Right? On top of these libraries, we provide concrete instantiations of many popular curves, as well as abstract constraint system API, which can be used to write your own circuits. And then above this generic constraint system interface, we provide many useful gadgets, such as lots of cryptographic primitives, as well as things that are just useful in normal programming, like signed and unsigned integers, finite field gadgets, elliptic curve gadgets, and so on. Right. Alongside that, we have a number of proof systems, and we're adding more, every few months, basically. And we also have verified constraints for these, so you can do recursive SNARKs, for example. Finally, using these generic interfaces, we've already implemented some useful applications, such as generic proof carrying data framework, which can be useful for developing your own recursive or succinct blockchain. We have an implementation of the ZK system, and as we'll see in the tutorial today, we have an implementation of a very simple rollup scheme. Okay. All right, so in this tutorial, as I said, we'll focus primarily on application development and circuit writing, but we'll see also a little bit about the other portions of the stack. Right. Okay, so the question is how to do SNARK application development in arkworks, right? So let's say you want to make your application. You have to have, as I said, two components, right? You have to have a SNARK as well as a circuit that you can plug into that SNARK. And so yeah, this basically breaks down your app dev into two steps. So step one, you have to sort of choose your SNARK and choose the elliptic curve. And step two is you have to sort of construct your circuit using the gadgets that we have, right? And now I'll show you like how arkworks makes both of these steps easy. Okay. So as I said before, we have a lot of SNARKs and curves implemented in the ecosystem, right? But the nice thing is that switching between these is really not, complicated. You could just have to basically switch one type parameter, and now you've gone from gross16 over BLS12377 to gross16 over the BW6 curve, or to BLS12381, or whatever you want, right? Now, let's say you don't like gross16 because it has trusted setup, circuit-specific trusted setup. You can easily switch from gross16 to, something which has simulation secure, simulation extractability. And then let's say you don't like your trusted setup anymore, you can go to universal setup such as Marlin, again, just by changing a couple of parameters. Finally, you can also, for example, switch from now universal trusted setup to trustless raw transparent setup by simply changing the kind of polynomial commitment. And again, all of this is, you can still switch between curves, switch between the kinds of circuits you're proving, and so on. Right. Okay, so yeah, so the point of this slide is basically to illustrate that arkworks sort of allows you to switch between, you don't have to concern yourself too much with the implementation details of the underlying curves or the underlying proof systems. You can easily switch between them if you need to. All right, yeah, so as I said, we can choose between many curves. What do we actually have implemented in arkworks? We have the very popular BLS12381 library, which is being used by many ecosystems such as Zcash, Algorand, and Ethereum. We also have BN254. We have this Tweedledee, Tweedledum pair of curves, which I guess now should be the pasta cycle, which is being used by Mina and also by Zcash. We have this sort of one-level recursion-friendly chain of BLS12377, which is being used by Cello and Alio to implement essentially verification of pairings inside a SNARK. And finally, we have these pairing-friendly cycles, such as the MNT cycles, which are being used by the Nimic folks. Okay, so this concludes basically step one, right? So what you've seen now is that we can easily switch between proof systems, easily switch between curves, and there's a large variety of curves to choose to fit your application, right? And you don't really have to concern yourself with the underlying implementation detail. You can just switch out like a type parameter and you have a new application. Okay, so now is sort of the more involved step, which is writing your application circuit, right? So sort of what SNARKs understand is this language called R1CS, right? R1CS is a low-level way to describe constraints over your computation in a way that is understandable with ZK SNARKs. So at a high level, like this is the mathy description of R1CS. It consists of these three constraint matrices, such that, and there's like a public input and a private input. And the idea is that sort of this input satisfies the matrices if this check holds. And what this check says is that A times Z, where Z is sort of the concatenation of X times W, with the element-wise product of B times Z equals C times Z, right? Okay, so now this is like obviously a very abstract and mathy description of a computation, right? It's not at all clear how to express useful computations in R1CS, right? Just using this prime mathy description. So what we try to do in arkworks to resolve this problem is to provide a high level and efficient circuit writing framework. So the idea would be that you express your computations in a way that looks very similar to native code, but in the end, it gets compiled down to this representation here, right? With circuits and variable assignments and so on, with constraint matrices and variable assignments and so on. Right? So do we actually achieve this? And I think the answer is like, it's not a sure shot, but I think in some cases it's very close. So for example, with this is a Krautseville multiplication, which is used in implementing some finite field arithmetic. But the point is that this is the native code, right, up above. So are there any questions? Let me just stop for questions. Okay. Okay, I'll take the questions, I guess, afterwards. Right, so yeah, so this is the native code. And on the bottom, we have constraint code, which looks almost exactly like the native code, right? Maybe there's like a couple of extra references. But the point is that now it's very simple to sort of look at the native code and be sure that the constraint code actually matches your sort of native spec, right? And this is also the case for like more complex primitives like hash functions and signature verification, as we'll see in the tutorial. Sort of our implementation of these matches the native version as closely as possible. Okay, so to actually make these libraries useful, you don't want to have to implement a lot of your reusable primitives again and again, right? So what we do in arkworks is we provide a solid library of a lot of popular R1CS gadgets spread across these three libraries, right? So we offer support for sort of standard programming data structures, such as Booleans, unsigned integers, as well as control flow and equality comparison, comparison and equality and non-equality checking and so on, right? So these are all like sort of the bread and butter of programming. On top of that, we provide gadgets for algebraic objects such as finite fields, elliptic curves, pairings, many different kinds, right? And these can be used to implement your high-level primitives such as hash functions like the Pedersen or Bow Hopwood Pedersen hash functions, your commitment schemes, SNARK verifiers, Merkle trees using these hash functions, Schnorr signature verifiers, and so on. So we have all of these implemented or like sort of in the process of being implemented in these libraries. And what this means is that when you go to implement your generic circuit, your application circuit, you can just take these components off the shelf and just plug them into your circuit without having to worry about re-implementing them. Okay, so these this toolkit has already been used for many applications. As I mentioned earlier, we have this generic PCD and implementation and this implementation of the ZK system, but also the Cello folks have been using our pairing infrastructure to implement a circuit verifier for BLS signatures, and they use this for their batch signature aggregation proof. So yeah, and I think I'm personally not aware of every application, but I'm sure there's like other people also using this framework to write circuits. Okay, so sort of that concludes our high-level overview of SNARK application development. But there's a lot more in arkworks, right? As I showed earlier, we have this very large and deep stack that is useful at every level of sort of the SNARK lifecycle. And in comparison to other libraries, I think in terms of the circuit programming front end, at least in Rust, I feel like we provide sort of a good mix between efficiency and ergonomics. So for example, we support non-determinism, whereas ergonomic languages such as Zinc, Socrates, Leo, often they're not able to easily support non-determinism. Or at the same time, we're also like relatively close to native code, which many other ecosystems, for example, libsnark or like the old version of Bellman, they're not able to match. In terms of the backend, we also have like a lot of curves, as those slides show, as well as a number of proof systems that you can instantiate and mix and match to suit your application. Yeah, so, and this is like, these libraries have been adopted in industry. So this is, I already said, it's been used by Cello and Aleo. It's also being used by Mina. I think it's also now available as a backend inside Socrates. If your company is using arkworks and our project is using arkworks and you want to be on the slide, let me know, and we'll be more than happy to put you up here. So thanks. Yeah, so this has been the joint work of a lot of excellent contributors at Berkeley, as well as external contributors. Sorry, there's too many to actually collate, but yeah, they've all been excellent. And we're always looking for new contributors. There's a lot of work to be done in the library and the ecosystem. So for example, massive integration, implementing new curves, new kinds of constraints and primitives. And we have pretty good support for onboarding contributors. So you want to get involved, please go to arkworks.org or ping me at this email or over Telegram, wherever. And I guess, yeah, now we can get to the tutorial. So that's available at this link again.
Thank you so much, Pratyush. Let's maybe take two questions on either of the two talks before we break into the breakouts. So I'm going to stop recording.